Hello everyone, welcome back. I'm your friend Insaxo. Today, we're going to know the lecture 4, Independence of Events and Bayes formula. In this lecture, we are going to know the independence of events, total probability formula, Bayes formula. Independence of events, definition. An event A does not depend on an event B if the probability of event B greater than 0. From the previous lecture, we know this symbol or this expression is called a conditional probability. But what does that mean? For example, this expression, we can read it as the probability that A occur given that B occur, or simply the probability of A given B. Now I could generally understand this line of sentence, the probability that A occur given that B occur. Remember that definition? So here it means that the probability of A given the probability of given the event B occur. If it's equal to the probability of A, that means what? That means no matter the event B occur or not, we will always get the probability of A, which means the event A and event B, they are independent. They does not affect the probability of each other. And from here, since we know that the event A and B, they are independent, so the probability of B given the event A occur would just be equal to the probability of B. So in the end, this expression and this expression will eventually equal to this expression probability of B times the probability of A. You want to get the intersection of them. And for this expression, if we want to use the English to describe it, that would be probability of intersection of independent events is the product of their probabilities. So if we get 3 events A, B, C, then we could get the intersection of event A and event B equal to the probability of event A times the probability of event B, or something like that. You can get it from those expressions. Then we will have an example here. This is an object.
Regular tetrahedron.
Regular tetrahedron. It's like a cube. For this one is toast. It is painted as follows. One face is red, another one is yellow, and the third one green, and the fourth one red, yellow, green. Basically, they have 4 different corners. 3 different corners, or maybe 4. Okay, so since it has 4 corners, why he only calculated 3 of them? Then he defined 3 events. If that cube fell into the face in a red corner, we call it event R. If that cube falls in a yellow corner, we call it event Y. If that cube falls in a green corner, then we call it event G. Basically, those are the first character of the corner. Events R, Y, G are pairwise independent but are not mutually independent. It is obvious that probability of R, Y, G equal to 1/2. You know what, I think this example is probably not a good one, since I cannot understand it in my imagination. But if you can understand the concept of independent events like this one, then that will be enough. Then we're going to get into the second concept, total probability formula. It is used in cases where an event A can occur only when one of the events, called hypothesis, H1, H2, Hn, and Hn does not equal to an empty set, that make up a complete group has occurred. Total probability formula lets the H1, H2 until the Hn be the complete group of events. These are mutually exclusive and exhaustive events. For example, the H1 are pairwise disjoint, and the U9 is the whole group, the complete group of events. And the probability of those hypotheses are greater than 0. So for each of the hypotheses, we know that each of the probability are greater than 0, is greater than 0. Then if A is any event, we get something like this. The probability of event A equal to the sum from I equal to 1 to I equal to n with this expression, which is the probability of the hypothesis times the probability of A given that the event of the hypothesis occur. This is the essential part of this definition.
High or pairwise disjoint.
They are pairwise disjoint, which means they are independent. I don't know. And then he got the proof A equal to A times the complete group of events. And the complex group of events would be equal to the hypothesis 1 until the n. We add it up together, and that's true. And since we are using the add symbol here, so we can extract those stuff out, so that we could get an expression like this one. Event A times hypothesis 1 plus whatever, and so on, where the summons of the last sum are mutually exclusive. Then by the sum rule for mutually exclusive events, we get something like this. I think what's the sum rule for that events? It didn't tell us.
Sum rule for mutually exclusive events.
So I'm gonna do a search. Alright, so guys, I got it. So basically, like what we normally would do in the programming, if we know that two events or two hypotheses or two conditions, they cannot happen at the same time, then we would use a symbol or to represent that stuff. For example, it can be A or it can be B, but they can be exact at the same time. So you do it like this. Then let's say since they are hypotheses, for those hypotheses they cannot happen at the same time, so they are indeed exclusive, mutually exclusive. And as we know in the algebra of probability, if we time two events together, that means we want to know the probability of the two events occur at the same time. But if we use the plus symbol, that means we just want to know the probability of either this one occur or this one occur. I don't care each one occur, but I'm just going to add them together, something like that. For example, this one, the hypothesis 1 and hypothesis 2, they cannot happen at the same time. But there must have one that would happen. Must have one that does not equal to 0, and we add them together. It's like using the OR operator. So for this one, it's the same. What we do is to add all of them together, and it's equal to the probability of event A, and then we could let's say represent the whole expression with this one. They are equal. First, if you look at the sum operator, then you will know that it's goes from n equal to 1 to n equal to n. That part is simple. Then we know that the probability of hypothesis is from I equal to 1 to I equal to n. There must have one that does not equal to 0. If it's not equal to 0, it must have some value out there. And for this probability, that means the probability of A given the hypothesis occur. So in other words, the whole expression, the meaning of the whole expression is that the probability of event A occur when the hypothesis occur. I know at the beginning you may feel really hard to understand this, but let me take an example. There were n white and m black balls in the container. Then one ball for unknown corner was lost. Then one ball is taken out of the container. What is the probability that it is white? So we're gonna try to calculate out the probability of event A, which is the ball that was lost is white corner. Is white, okay? Then the hypothesis is we may have the white ball lost, or we may have the black ball was lost. Basically, we had two hypotheses. And for the first one, what's the probability of the white ball was lost? It depends. For example, for the total number, we got n white and m black, so we got n plus m numbers of the whole ball. And since we got n white, so it could be just equal to the n divided by the whole number. This concept is quite simple, right? We all could understand that. And for the black ball was lost event, we have something like this. This is also quite simple to understand. Then we go on. We know that the hypothesis 1 plus the hypothesis 2 will be equal to 1. Why? Because there only have two conditions, only have two hypotheses. There has no other probability. There has no other way that it could be some other corner, since we only got the white and the black balls. Okay, then we're gonna go on. The probability of event A, given that the hypothesis 1 occur, which means for this condition, for this probability, I mean, for the event A occur by what? Based on what? Based on the hypothesis 1 occur, which means the white ball was lost. So what's the probability of that? Since we know it would be just equal to the n white ball minus 1 divided by the whole number of ball minus by 1. Why? Why do this? Because the white ball was lost. So at the beginning, it has n white balls. But after one white ball lost, then we have n minus 1 balls. That's why we write this expression. And also for the black ball, since the event A, the event A is one ball is taken out of that container, and if that's if it's a black ball that was lost, then it will not affect the white ball that we have, so we still have n white ball, but for the whole number, it has to minus 1 because we got one ball lost. And then, based on the two hypotheses, since we know the two hypotheses, the probability of that of the two, then we could just use a total probability formula to get the probability of A, which is we just have to use this formula. The probability of the hypothesis times the probability of A given the event hypothesis occur. So if you look at it carefully, you would know this one is the probability of the hypothesis 1 times the probability of the A given the hypothesis 1 occurs. And we do that for both hypotheses. Eventually, if we do the calculation, we'll get this result. I guess what this formula does is to just give us a way to find out the probability of A if we know all those hypothesis probability, and when that hypothesis occur, the probability of A at that special parse. For example, when that hypothesis occur. And by sum all those events or all those probability together, we get the whole probability of event A occur, no matter what hypothesis that was happening out there. Something like that. And for now, I still, let's say, even if he have a proof out there, but okay, I do not think that. Alright, so we assume this is correct. Then how he transferred this expression to this expression, how he did that. Alright, if you look carefully, you would know this one just represents the probability. Let's say this just means the probability of event A and hypothesis 1 occur at the same time. They both happen, and we just want to get the intersection of the event or of the probability. And that's true if you think about this expression. They are basically doing the same thing. For example, the probability of hypothesis happen, then the probability of event A when the hypothesis happen. So in the end, no matter what he do, he's getting the intersection of the two events. The probability, the event A and the hypothesis, two events, they are happening at the same time. Something like that. So they are represent the same thing. Okay, so this is a total probability formula. Let's get into the third one. The third one would be generally more difficult since it's called Bayes formula. People always love to I just think that this one is quite famous. We often hear people say
Bayesian formula.
贝叶斯公式
Yeah, we often hear people say this one, but we never know what it is and what it can do or what it does in the mathematics or in our real life.
Bayesian formula.
Bayesian formula, alright, or Bayes formula. Suppose that we get so many different hypotheses from H1 to Hn.
Hypotheses.
Hypotheses. I guess I'm reading it wrong, so I'm gonna do some practice about it.
Hypotheses.
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 Hypotheses. Alright, let's go on. So we have all those hypotheses. It's a complete group of events. And the event A is some events, and the probability of this event does not equal to 0, which means it's greater than 0. It cannot be a negative number. Yeah. Then the conditional probability that the hypothesis H1 took place. If event A was observed as a result of an experiment, can be calculated by the formula of this. So what does this mean? It means the hypothesis 1 occur. It means the probability of the hypothesis I, given that the event A occur, is just equal to the probability of the HI, which is a hypothesis, times the probability of A given the hypothesis occur. Here he just want to do a proof about it, so he used a product rule, but I almost forgot about that, so I'm gonna do a search about it. Product rule probability. So the product rule is the probability of intersection of event E and F equal to the probability of E times the probability of F. Yeah, that's correct if the E and F are events that are independent. But how it is related to this one? Alright, so what I mean here is that if he want this to be true, then the event A must equal to this one. But how can it be equal? It only equal if the event A does not depend on the hypothesis, or in another words, they are independent. They are not, let's say, rely on each other. And since they are independent and they are not rely on each other, so for the probability of this kind of stuff, it will be equal to the probability of hypothesis. So in the end, we can just use an equal symbol to connect this expression with this expression. And then we could, let's say, convert this expression into this expression if you know some basic mathematics. Yeah, this one equal to this one, then this one equal to this one. After that, this one equal to this one. They are identical. Then we use the total probability formula, which we just know that in here. The probability of A equal to the sum of all those hypotheses and its corresponding probability of A given the hypothesis exist or occur. So that's why we get this, and they call this kind of thing the Bayes formula. Okay, only talking with, let's say, if we only know those formulas, that would have no meaning for us, since we will not remember those formula. We will not do that. We will only use them when we need them, and we will do the check with Google or something like that. So we don't actually need to remember those formulas, but we need to know how to use it or what's the meaning of it. Because if we do not know the meaning of it, then we cannot use it, right? Since we don't know what it is, then how can we actually use it? That makes sense, right? So to understand it is the key for everything. We don't need to remember it. We just had to understand it. That's it. So that's why we need a lot of examples. Those examples would help us to understand the real usage of it. For example, here's a map. Yes, we all know that it's a map. A tourist who does not know the way sets out from the point O. It starts from this point, this one, and goes along one of the 3 roads and gets to the point A. Here's the point A. Find the probability that he went along ice pass I equal to 1, 2, 3. For example, this is the first way out, and this is the second way out. This is the third way out. So find the probability that he went along ice pass. So what is that? What is the probability that what is the event that we want to get the probability of? So event A is the tourist gets to point A. Okay. So we need to get the what? Okay. So we need to get the probability of this tourist goes to this way, hypothesis 1, hypothesis 2, and hypothesis 3. We want to get the probability of this tourist take each road. Will it take this path? What's the probability of it? Will it go in this way from the O to H2? Will it go this way? What's the probability of that? Will the tourist go and pick up the hypothesis 3? What's the probability of that? So in the end, what we want to get is the probability of the hypothesis 1, 2, and 3. And only by having that is not enough. We also need to make sure that the tourists eventually get into the target point, which is the point A. So in other words, we need to first make sure that tourists get into the point A. Then what's the probability of this tourist go this road, or go this road, or go this road? Something like that. And we're gonna try to solve it by using the Bayes formula. How can we do that? We got first we define an event, which is the tourist gets to the point A. That's the destination for that tourist. And then we got a few hypotheses, I guess.
Hypotheses.
We got 3 hypotheses. The H1, which is the tourist goes along the one's road. And the hypothesis 2, the tourist goes along the second road, which is this road. And the third one, the tourist goes along the third road, which is this road. And obviously, the probability for this tourist to pick one of that path or one of that road have the same probability, 1/3. Why? Because if that tourist was in this point at the first, then he basically only have 3 options. Since there only have 3 roads, he cannot go third road because there has no fourth road. So he only got 3 options, and for each option he choose, the probability of it is 1/3. I think this is quite easy to understand for now. And yeah, that's it, and let's go on. Let us calculate the conditional probability of this tourist that if he can get into the point A based on different hypotheses. So at the first one, if that tourist can get into the point A when he goes into the first road, what's the probability of the tourist that if it get to the A? It says 1/3. Let's say if that's true. So if that tourist goes into this way, he will get into this point, and when he get into this point, he got another 3 options to choose, and there only have one way that he could get into the point A. So when he get into here, the probability of this tourist getting to A would be 1/3 since he got another 3 options out there. So 1/3. He only got 1/3 probability to get into the point A. Okay, then how about this one? The probability of this tourist get into A if he took the second road. What's the probability of that? It's equal to 0. Well, it's quite simple because if that tourist take the second road, he will get into here, and when he get into here, he will find that he has no options at all since there has no road that will lead him to the point A. So the probability for him to get into the point A is 0 since he have no choice. There has no road for him to pick. So let's look at the third one. What's the probability of the tourist getting to the point A if he took the third road? It's equal to 1. Why? If we look at this map carefully, you would know when that tourist chooses the third road and when he get into this point, the probability for him to get into A is 1. Why? Because there only has one road left for him to choose. He have no other choice but to choose this one. So no matter what he choose, he will always get into the point A. So the probability for this tourist to get into the point A when he chooses the third road is just 1. So therefore, by the total probability formula, we would know the probability of the tourist getting to the point A is equal to something like this. Why? Yeah, always ask the why. So we're gonna look at the total probability formula. It's equal to something like this, we're gonna all those hypotheses times the hypothesis occur the probability of the event A. Yeah, that makes sense. That makes sense since we are using the product of the two probability, which means we want to get the intersection of them, and that's definitely correct. For example, first we know that the hypothesis will occur, and then we know when that hypothesis occur the probability of A. We want to know the two probabilities intersection or something like that. So we use the product. We use a term here. They didn't draw it out, but you would know it's a product of the two probability. And in this case, let's say why he do this. We all know the probability of A when some hypothesis occur. That's for sure. So we got something like this. And then since we all know the hypothesis equal to 1/3, so whenever for each element inside of this, we're gonna time it by 1/3. This 1 times 1/3, 0 times 1/3, 1 times 1/3. If we put them together, we would get it something like this, and we time the whole stuff for 1/3. So at the beginning, this may seems to be not correct, but eventually if you do some transformation for it, you will know that it just matches the total probability formula. So in the end, for this tourist, what's the probability of him eventually get into the point A? Well, it's 4/9, okay? But only by knowing the probability of event A is not enough, since that's not what we really want to get. We want to find out the probability that he went along each path. For this 3 of them, we are just trying to get the probability of that tourist will get the point A, but it's not the probability of this tourist pick one of those roads. If we want to know that, if we want to get the probability of this tourist pick each road, then we will have to use the Bayes formula. That's where this formula shines. That's where we need to use the Bayes formula. So how do we do that? We say the probability of that tourist took one road when he eventually gets into or after he eventually gets the destination point A is equal to this one. Well, this one, if you don't know that, let me just back into here. This is what we have. For this one, it's just equal to something like this, the probability of A. This formula and this formula, they are the same thing, I guess. So since we already know this one, probability of A, we just calculated it out. All we have to know is this part. The probability of the hypothesis times the probability of the event A occur. Of the event A when the hypothesis occur. And if you take a look at this one, you will know that just the same thing that we are talking about. So anyway, this is mathematics. In the end, if you're only looking one formula or one expression, you will have no idea what's going on in the mathematics. You have to go back to look at each variable and each formula, how it is composed, how they generated that expression. You have to back look for all those details to be able to understand why this line is equal to this. So let's say it's kind of like the programming, but it's definitely harder than the programming stuff because when you look at those programming code, you don't have to memorize so many things. You just have to, let's say, you just have to go back and look at those code, and sometimes I think you don't even have to memorize it, because in the programming language you can always call a higher level of function. You don't have to remember what the function does in all details. All you have to know is when you should use that function and what is the function name and how to use it. And then that's all. You don't have to care about those details inside of that function. But in the mathematics, you kind of have to know that. Otherwise, it can be, let's say, I don't know. It's kind of similar to the programming language, but it's definitely much more harder than that. Okay, then this is today's learning for the mathematics, and I hope you enjoy this one, and good luck with your exam. See you next one. Bye.